Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Homework for lecture 110. All right, let's start with problem number 1. See what we have here. A type 1a supernova is known for its rapid rise in brightness following the explosion. Suppose the luminosity, brightness, B of t, of the supernova increases exponentially according to the usual exponential increase formula, where B0 is the luminosity at the time of first detection, t equals 0. K is the constant growth rate in inverse days, and t is the time in days since first detection. Observation of a particular type 1a supernova suggests that at t equals 0, the brightness is approximately 1 times 10 to the 9 solar luminosities. After 17 days, roughly the time it takes for the supernova to reach peak brightness, the brightness has increased to 3 times 10 to the 9 solar luminosities. Part A, determine the growth rate of the growth constant kappa, or K. And then part B, using your result from part A, estimate the brightness of the supernova at t equals 23 days. It is kind of a wordy problem, but it is actually kind of easy to work out. So let's start by writing down B of 0, B of t equals 0, is equal to 1 times 10 to the 9. And then this symbol here, L with the subscript, circle, and dot, that's solar luminosities. And then we also have that B at 17 days is equal to 3 times 10 to the 9 solar luminosities. And we can also write this as equal to 1 times 10 to the 9 solar luminosities times e to the 17k. And so now we just need to solve for k. So we'll have that e to the 17k is equal to 3, because the 10 to the 9s are just going to cancel, as will the units of solar luminosities. And so this implies that k, just by simply taking the natural logarithm on both sides, we'll get that this is equal to the natural logarithm of 3 over 17, which is approximately 0.065. Okay, so that's part A. And then we use that result for part B, and we want to know what is B at 23 days. So what is B at 23 days? Well, that's going to be 1, that's B naught, 1 times 10 to the 9 solar luminosities, times e to the ln 17 over, oh no, ln 3, sorry, ln 3 over 17 times, not t, but 23, times 23. And that will be equal to, if you just simply, well, let's see, we can write this out a little better. It's going to be 1 times 10 to the 9 solar luminosities times e to the ln 3 raised to the 23 over 17 power. I'm just doing a little manipulation of the exponents and the properties of logarithm. E to the ln 3, well, what is that? That's just 3, right? So that gives us that we're going to get 3 times 10 to the 9 solar luminosities times, it's 1 times 10 to the 9 times 3 to the 23 over 17. And this is approximately, if you plug it into your calculator, 4.42 times 10 to the 9 solar luminosities. Okay, let's take a look at number 2. Number 2, when living, organisms maintain a constant ratio of carbon-12 and radioactive carbon-14 because carbon-14 is continuously replenished. After death, however, no new carbon-14 is absorbed and its amount decays exponentially. The half-life of carbon-14 is 5,730 years. Archaeologists have discovered charred logs at an old fort. Analysis shows that the logs now contain only 70% of the carbon-14 that living matter would have. Assuming the fort was constructed using freshly cut logs and that it burned shortly after construction, determine approximately how many years ago the fort burned down. Okay. So, number 2. So let's write a function n of t equals n naught times e to the minus kt. Why the minus? Because this is an exponential decay problem. Now, the half-life, e to the minus k, and we'll write t sub half, should be equal to 1/2. This implies, of course, that the rate constant k is equal to ln2 over t 1/2. This we had in class, by the way, right? And so we know that this half-life is 5,730 years. And so that means that the decay constant is going to be ln2 over 5,730. And that is approximately 0.000121. So now we have a decay rate. And if we write n of t over n naught equals 0.7, because that's what we observed, then this will have to be equal to e to the minus ln2 over 5730, which is just this number here, times t, because we don't know what that time is yet. So this would imply that t should be equal to minus ln of 0.7, that's the 0.7 here, divided by k, the decay constant. This will be equal to minus ln of 0.7 over ln2 divided by 5730, which is the same thing as, let me write it over here, 5730 times ln of 0.7 over ln of 2. Now let's note that ln of 0.7 is the same thing as ln of 7 over 10, which is equal to ln of 7 minus ln of 10, which is, of course, going to be negative. Now, which means that ln of 0.7 will be positive. So if I simply plug these into my calculator, I should get that t, taking this ratio, is equal to 2,950 years. All right, number 3. Verify that q of t equals c times e times the quantity 1 minus e to the minus t over rc that satisfies the differential equation dq dt equals e over r minus q over rc. All right, number 3. So let's say that if q of t is equal to c times e times 1 minus e to the minus t over rc, then dq dt is equal to c times e times 0 plus 1 over rc times e to the minus t over rc. And this, of course, just equals e over r times e to the minus t over rc, because the c and the c here cancel, and we're just left with e over r times this exponential. So now we'll calculate e over r minus q of t over rc, just by plugging this in. So that's going to be e over r minus 1 over rc, and we're going to plug in for q of t, which we have up here, and that'll be c times e times 1 minus e to the minus t over rc, which equals e over r minus e over r plus e over r times e to the minus t over rc, which equals e over r, because these just cancel right here, times e to the minus t over RC. And since both sides, this will be one term that we've calculated using the formula, and this is the derivative that we took of q in the first place. And since both of them are equal to the same thing, we've confirmed that they are equal to each other. And so that's how you show that this solution does satisfy the differential equation that you were given. Okay, that's 3. Number 4. All right, so we have a 5 microfarad capacitor is charged to 200 volts and then connected across a 100 ohm resistor. We want to know A, what is the initial charge on the capacitor? B, what is the initial current for discharge? And C, what is the time constant for this circuit? And then finally D, how much charge is on the capacitor after 1 millisecond. I think this is pretty much identical to the problem we worked in class. Let's see. We'll definitely want to have a circuit diagram here. So let's draw a circuit diagram. So we've got a 5 microfarad capacitor. Okay. Here is our 5 microfarad capacitor. It's charged at 200 volts. Okay, and so it's at 200 volts. And is it connected across a 100 ohm resistor? Okay. 100 ohms. All right, I guess that's all it is. All right, so part A asks what is the initial charge on the capacitor? Okay. Initial charge would be Q naught. It's going to be equal to C times V naught, which is equal to 5 microfarads times 200 volts. And that, multiply through, will be 5 times 10 to the 6, 5 times 10 to the minus 6, times 200, so that's 1,000 times 10 to the minus 6. It's the same as 1 times 10 to the minus 3 coulombs, which is, I guess, 1 millicoulomb. Okay, what about part B? Oh, I should note this is problem number 4. Part B asks, what is the initial current for discharge? Okay, so I naught, this is just Ohm's law, right? I naught is going to be equal to V naught over R, which is just 200 volts over 100 ohms, which is just 2 amps, right? Yeah, 2 amps. Okay, part C. What is the time constant for this circuit? Now we want to know what K is, or not K, RC. We want to know what RC is. So call it T, RC. It's just equal to RC, which is just equal to 100 ohms times 5 microfarads. And so that is going to be equal to, well, 5 times 100, it's 500 microfarads, which would be 0.5, not microfarad, what, stupid, seconds, microseconds, which is 0.5 milliseconds. Okay? And then the last part, D, how much charge is on the capacitor after 1 millisecond? Okay? D. Well, we use our formula, Q equals Q naught times E to the minus T over RC, which will be 1 millicoulomb times E, 1 times 10 to the minus 3 seconds. That's 1 millisecond. And then our time constant RC, which we got from before, which was 0.5 milliseconds. So those units, I should have made it the same. 0.5 times 10 to the minus 3 seconds. Well, I can write that better. It'll be 5 times 10 to the minus 4 seconds. That's probably a better way to write it, right? And that's going to be equal to 1 millicoulomb times 0.135. So that is equal to 0.135 millicoulombs. All right, problem number 5. We've got the circuit diagram here, which I'll reproduce here in just a second. It says initially the circuit shown is uncharged with the switch open. The switch is closed at t equals 0. What is the initial current? Find an expression for the initial current through the circuit a long time after the switch is closed. So let t go to infinity. C, find a general expression for the current at any time after the switch is closed. And then D, once the capacitor is charged, you can assume 99% or t equals infinity, whatever you want. The switch is again open. How long does it take for the capacitor to discharge to 10% of its initial charge if R1 equals R2 equals 1 kilo ohm and C equals 1 microfarad? Okay, so we won't use these numbers in the first part of the problem, but at the end of the problem we will. Let me draw the circuit here. So we've got an EMF, which later we'll make equal to, do we assign? I thought we had given, well, maybe we don't need it. Minus, here's our EMF. And we have a capacitor, capacitance C. We'll need a switch. And I'll draw it both in the open and closed position. And then we need a resistor. Resistance R. Oh, I missed a resistor. That's probably important, huh? R1, and this is R2. Okay. This is a tricky problem. So, part A, this is 5. Part A is asking, what is the initial current? Okay, so that's basically, it's a short circuit. So, when this is short-circuited, you can kind of think of it like this. That's a terrible drawing. R1, R2, such that we'll have an effective resistance or equivalent resistance. I never know which one to use. Is it equivalent resistance or effective resistance? And what's the difference? And this, of course, you'll remember is just R1 times R2 over R1 plus R2. It's just the parallel resistors formula. And so this would imply that I naught, using Ohm's law, is just equal to the EMF over this. All right, I'm using both now, effective and equivalent. Okay, I'll just change it here. R equivalent, which you can then write as E times R1 plus R2, all divided by R1 times R2. So that would be the initial current. B. Find an expression for the current through the circuit a long time after the switch is closed. So I would say that as t approaches infinity, right, the capacitor is charged, meaning no current flows through R1. So you've got no current going through R1 if this is completely charged. And that's what happens at t equals infinity, right? It's completely charged. So in that case, you could get that I infinity is equal to epsilon over R2. So that would be an expression for the current through the circuit a long time after the switch is closed. It's effectively just going through R2. All right, part C. Part C asks, find a general expression for the current any time after the switch is closed. That is a tough one. Essentially what you want to do here is apply Kirchhoff's rules to this circuit. You're going to get a differential equation, and if you solve that differential equation for the charge and then take the derivative so that you get the current, you're going to get something that looks like this. I of t will equal I of infinity plus I naught minus I of infinity times e to the minus t over RC. This is important, the R1C. Let me write that bigger so that you can see it. Over minus t over R1C. And that, of course, is going to be epsilon, or E, over R, where did I just wrote R2. I infinity I substitute in, plus I naught I had from up here. I don't need the parentheses. They give me E R1. I'm going to do a little factorization here. R1, R2, E to the minus t over R1C plus E times R2 over R1 R2 times E to the minus t over R1C. And then we have one more term I didn't have enough room. Minus E over R2 times E to the minus t over R1C. And this, we can factor out an E over R2 as follows. I want not a curly bracket, but a regular bracket. Get 1 plus E to the minus t over R1C plus R2 over R1 E to the minus t over R1C minus E to the minus t over R1C. And so you can see that this term and this term cancel. And so that all we're left with is E over R2 times 1 plus R1 over R2 E to the minus t over R1C. Okay. Now, if you want some insight into how to solve, you apply Kirchhoff's rules to come up with a differential equation, which gives you this expression for the current. Maybe I can write that up in paper form, because I think it would take a while to write up on the board here. But this is the answer you should get if you get it right. But let's move on to the last part. Part D. As once the capacitor is charged, the switch is again opened. How long does it take for the capacitor to discharge to 10% of its initial charge if R1 equals R2 is 1 kilo ohm and C is 1 microfarad? All right, so we have part D. Can I see this on the screen? Oh, we're very low, very close to the bottom here. So I tell you what I'm going to do. I'm going to erase up to here. I don't want to run out of room. Hopefully this will clean up a little bit. Because we're going to need the room to write. Okay. Yeah, and so we'll let R1 and R2, what did I say it was? 1 kilo ohm. 1 K ohm, 1 K ohm, and the capacitor is 1 microfarad, 1 microfarad. So this is part D. So once the switch is open, the capacitor discharges through R1 and R2. That's what it does essentially. So once the switch is open again, so now the switch is open, which takes the battery out of the equation. That's why I didn't have a value for the EMF. And so we can forget about this part of the circuit, right? It's irrelevant now. So I'll just remove it from the diagram. And so this is basically the picture that we have. So Q of t will be equal to Q naught times e to the minus t over, call it tau sub d, where tau sub d is equal to R1 plus R2 times C. It's just the RC time constant, but we have to use both resistors, right? Because these two resistors are in series. And so at 10%, that's 0.1 times Q naught will equal Q naught times e to the minus t over tau sub d. This implies that the natural logarithm of 1 over 10 is equal to minus t over tau sub d, which in turn implies that t is going to be equal to minus R1 plus R2 times C times the natural logarithm of 0.1, which would then equal, we're going to get 1,000 ohms plus 1,000 ohms again, times 1 times 10 to the minus 6, and then doing ln1 minus ln10 and taking the negative of that, we'll get 2.302 approximately, and that gives me a time of 4.604 milliseconds. Okay. So I think part C was probably the trickiest part, and again, I'll probably write something up and post it so you can see some details on how exactly to apply Kirchhoff's voltage rules to that circuit and come up with a differential equation whose solution will give you the current as a function of time. If I can remember to do that. If I forget, somebody post and let me know that I didn't do it, and I'll make sure it gets up there. So that's it for the homework. I'll see you next time.